The fact, as we saw earlier, that delta x is proportional to the square root of delta y suggests a constant time of fall and implies a constant horizontal velocity. We'll work through the details later, but just the fact that delta x is proportional to the square root of delta y suggests these two ideas. That the time of fall when the ball comes off at a horizontal is constant, and the horizontal velocity is therefore constant. So the picture ends up looking something like this. Ball rolls down the ramp, gains a certain kinetic energy, comes off at a horizontal, is pulled by gravity, accelerated downward by gravity so that it moves faster and faster downward while moving horizontally at a constant velocity. So we have a constant horizontal velocity, vertical acceleration g, and the vertical motion and the horizontal motion happen independently of one another. In the situation that we measured in the lab, the data that we actually took, we had a 94 centimeter drop. The delta x was 9.1 centimeters, then 15.1 centimeters, I believe, then 20.3, something like that. We can put all that information together with a calculation of the delta t required for a 94 centimeter fall. Okay, if an object falls 94 centimeters, now the vertical motion is characterized by the fact that the vertical velocity is 0 at the instant the ball leaves. So vertically, we start at velocity 0 and accelerate downward at 9.8 meters per second squared. Accelerate downward at 9.8 meters per second squared, or 980 centimeters per second squared, until the ball strikes the floor 94 centimeters below. This tells us that we know delta S, we know V naught to be 0, which allows us just to get rid of this term because 0 times delta t is 0. That just becomes 0, so the right-hand side just becomes 1/2 at squared. And we know the acceleration to be 9.8 meters per second squared. So we can easily solve for delta t. Multiply through by 2 over a, and take the square root. We get delta t is the square root of 2 delta s over a. Actually, it's plus or minus the square root of 2 delta s over a, but since time is running forward, we know to take the positive result. This gives us a delta t of 0.44 seconds, and we can then put this delta t together with our observations of delta x and our assumption that the horizontal velocity is constant, and we'll be able to determine how fast the ball is moving horizontally from each drop.